So we actually divide our time response analysis into two parts. We look at what we call this, which is transient response, and then we also look at steady state response. There are two parts to our analysis when it comes to time response. But this section is going to be about transient response. The transient response is a time response that decays over time. So it just happens for a short bit when the system's responding to either an input or to a disturbance and trying to stabilize itself or get itself back to a constant state. And then the steady state response is that constant state it gets back to. So whenever a system is subjected to a change in its set point, or whenever a system is subjected to a disturbance, it will, if it's a closed loop system, it will attempt effectively to restabilize to a constant value. And that constant value is a steady state response, but there is a time, a kind of processing time whilst it adjusts itself, tries to bring itself into that steady state condition. And that's called the transient response. So we're looking here at the transient response. In lecture 4, we looked at an RC circuit, as I told you, and then the simplified DC motor. And we learnt about those and how they are represented as first order transfer functions. And this is the general form of a first order transfer function. Well, we looked at two different forms. This one we're calling the time constant form, and the other one is called the ZPK, which actually stands for zeros pole gain form. But this one is this time constant form. And we just rehearsed actually that the values for tau, our time constant, and k, the open loop gain, are dependent on the properties in the system. So in the case of an electrical circuit, the resistance and the capacitance in the circuit. In the case of a mechanical system, the inertia or the mass that you're dealing with in the system, etc. So those are the kind of elements that will affect what our time constant is and what our gain is. And we also saw this before, which is the standard first order response. I think we looked at this when we looked at applying a step input to our DC, to our RC circuit, sorry. So this is the standard response to a step input for a first order system. And this can be any first order system. It doesn't matter what type of system it is. If it's categorized as a first order, you can determine a time constant. You can express it in this form. You can get this curve. Right, this is the response of this system, first order type system, to a unit step input. Because it's a first order, it will only have one exponential term in the time response, the output time response. The 1, this comes from the step input. This is a unit 1 step input. Right? This part, this comes from other elements of the system, the time constant and so on. Now, whenever you have a standard first order system subjected to a step response, you get this same curve, which you can normalize. So we've normalized it here for a unit step input, and we've normalized the time frame into, in terms of tau, the time constant. So you can say this is 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. Now 1 tau, we always get 63.2% of our final value. It's a first order system subjected to a step input. At 2 tau, we always get 86.5, 3 tau 95, 4 tau 89.2, 5 tau 99.3. At 4 tau, we can more or less say by the time it's got within 2% of the final value, it's achieved its final value. So you could say this 4 tau is really the time to the system no longer being transient, and now it's being steady state. So if we say that, then all of this up to that point in time, this is transient, because this is the system responding to a change, which is the change in the set point, and trying to get to a steady state condition. And then from here onwards, we're going to call this steady state. The same applies for a ramp input. So this is a ramp input, which means basically input equals output. This line sort of converges to a straight line. The straight line starts at tau and goes up at the same one-to-one gradient. But it doesn't sort of converge immediately to this straight line. There's actually, you could divide it between parts again, and we could say this for a ramp input. This element is the transient element, and then after that we're into steady state. So for a ramp input, steady state is the system ramping up its output in a way that corresponds to the ramp rate of the input. And you can see here, this is the equation for the output. Now we've got a more complex input because it's a ramp, and the ramp gives you this t. It gives you actually an output of t minus tau. These two will remain. These are steady state elements because they don't go anywhere. Whatever value of t you choose, whatever value in time, whether it's 1 or infinity, you're always going to have these elements in the output equation. But this one here, you see this as an exponential, a negative exponential or decaying exponential. So this is going to disappear after a short while. And that will be our transient. So now, see our steady state, and we have a steady state error here. The steady state error is tau. You can express that either in terms of the steady state output error or the time lag between the input and the output. So we also just looked at the mass spring damper system, and we got the second order, the prototype second order transfer function. We looked at this normalized form. We learned that you could express it in terms of something called a natural frequency, something called a damping ratio. In the normalized form, the transfer function doesn't matter where it comes from or what type of system it corresponds to. It could be an LRC circuit, it could be the dynamics of an aircraft, it could be a cruise control system. Doesn't matter what this plant model is representing. It's always going to have a natural frequency and a damping ratio that can describe it, right? Or describe the dynamics of the system in response to a given input or a disturbance. If we set our damping ratio to 0, right, then this term is going to be eliminated. Assume that zeta equals 0, so there's no damping whatsoever. There's nothing sort of mitigating the oscillation in our system. Then what will happen then is that the system will oscillate with constant amplitude. So this is a handy little tool. I'll put the link in the notes, that allows you to actually plot the output of a system for varying values of gain k. Well, you can see the transfer function here. K is like just a pure gain, so I'm going to set that to 1. And damping ratio and natural frequency. So I'm going to set the damping ratio to 0. So it's just like a little online tool. Let me actually... So if I set this damping ratio to 0, what do you think is going to happen? All right, I'm sure you got that right. Simple harmonic motion, right? Just see it, the simple harmonic motion pattern here. In other words, this system, this oscillation is not damped. It's going to just continue to oscillate at that same amplitude or at the same magnitude, basically for infinity. Right, so that's, if you want to get a sense of the output of any system, you know the damping ratio and natural frequency, you can always turn to this little tool. Quite a neat little tool there. If the system has no damping, 0, then it's cycling or it's vibrating in simple harmonic motion, and that simple harmonic motion is termed marginal stability. So it's right on the edge of being stable. If you put any more energy into the system, it would become unstable. If you take energy out of the system, it will start to converge to a settled value. It would be damped, in other words. But if we add any energy, it's going to become unstable. And so that omega n is the natural frequency of oscillation of the system when damping is set to 0. And remember, omega n is expressed in radians per second, right? So let's look at our damping ratio now. And our damping ratio does have a very significant, obvious effect on the time and on the frequency response. Reducing the damping ratio will make the system more oscillatory to a level that we just looked at. If you have a 0 damping ratio, the system's purely oscillatory, it's marginally stable, and it's just oscillating in simple harmonic motion. If we increase our damping ratio from 0 to 1, that gives us what's called an underdamped system, which means it's going to have some oscillation, or should have some oscillation, when a known input is applied to it. If we set our zeta damping ratio at 1, it's what would be called critically damped. If our damping ratio is above 1, it's overdamped, and that means it's very sluggish in its response. Right? The system becomes very sluggish. Zeta is typically in the range of 0.4 to 0.6. So if you're wondering what kind of zeta values you might want, then that will give you a nice little fairly crisp response with a bit of overshoot, but nothing too extreme. So if we apply now a step input to our standard second order transfer function, and we take inverse Laplace transform, so we're applying a known input R, which is 1 upon S. So this is our output Y. We've had our input, our step input applied. If we have that standard step input to a second order transfer function, standard second order transfer function, this rather complex equation is our output yt. So yt is the inverse Laplace transform of y of s, and it's equal to this: 1 minus some coefficient which is a function of zeta times an exponential term minus zeta omega nt times the sinusoid omega n root with oscillation at frequency of omega n root 1 minus zeta squared times t minus a phase shift of cos the minus 1 of zeta. Right, so we can break this down. It starts from 1. Where does this come from? Well, actually, this step input produces that 1. Right, but then we have an exponential term. So this means that everything else is decaying. So eventually, we could say y of infinity equals 1, because as time increases, then this exponential is going to get closer and closer to 0. So all of this part of the equation is going to disappear. This whole thing is going to disappear. So this whole thing that I've just encapsulated in my green squiggly line is a decaying part. It's diminishing over time. But whilst it's in the process of diminishing, you see it behaves as a sinusoid. So it's actually oscillating. And what's going to happen is as time increases, then the magnitude of the oscillations, because this is really, this is the magnitude of your sinusoid. Let me do it in blue. Right. This is magnitude of the sinusoidal oscillation. Right. So your sinusoidal oscillation will continue at the same frequency, right? And it will continue with the same phase shift. But as time goes on, the magnitude of that sinusoid is going to be decreased. So if we simplify this a bit, and we're going to say, well, let this term equal A, let this term equal C, let this term equal B, this one we're going to call alpha, right? So simplified it down. So A is our, is given here, B is given here. And this is all true for zeta less than 1. So if you have an underdamped system, in other words. Once that zeta is less than 1, then we get these expressions for the different parts of that overall second order system response equation. These give us a hint as to how we can analyze certain characteristics of our second order response. And this is a typical second order response, and the important one, this is the blue line is really our output CT. So you can see it's got this sinusoidal shape, but the sinusoid is decaying or reducing in amplitude as time goes on, and it's decaying within a shrinking window. So you see there's a decreasing exponential here, there's also an increasing exponential here, and that basically creates a window within which your sinusoid is decaying. And there are characteristics we can draw from our sinusoidal response. The first is our peak output, right, which is this point here. Our peak magnitude is given by e to the minus zeta over 1 minus zeta squared times pi. And these, you can see how, I'm not going through the process of directly deriving each of these expressions because we don't need that for the course. But I just wanted you to be aware of where these came from. But you can see the form of those equations here in the magnitude term of this sinusoidal element. The magnitude really is a e to the minus ct. And so the peak magnitude will occur at a certain point in time. And when that occurs, you can calculate the MP. But you can also calculate the time to the peak. And the time to the peak is given by pi over omega n root 1 minus zeta squared. That rings a bell because this part is here. Right? It's the sinusoidal is B. It's the frequency of our sinusoidal oscillation. So you can see that this is something pi over the frequency of our sinusoid gives us the time to peak. This term, omega n root 1 minus zeta squared, which we call B just above, is also known as omega d, or our damped natural frequency. So our time to peak is pi over our damped natural frequency, and that gives us this time, right? Is it? We're looking at the time from 0. Let me try to make sure this lines up here. To time peak, time to our first peak. Another important characteristic of our time response of a second order system is how long does it take to settle. And you could have different criteria here. You could have, well, I want it to settle within 1% of its final value, 2%, 5%. If you're being generous, you could look for 10%. 2% is reasonable enough, I think, in most cases, right? But here, this is showing the settling time for 5% of the final value and the settling time for 1% of the final value. The settling time for 5% is 3 times omega n zeta. Again, you can see that comes in here, right? It comes in at the coefficient of the exponential term. So it's intimately connected to this decaying window, which makes sense because this window, this sort of decaying curve, these are exponential terms bounding the amplitude of our sinusoidal response. We do this sinusoidal response. The green line here, no, it's not green. The green line here, this is our actual output. Right, and the output is bounded by these two exponential terms in blue. And well, you know, because if we want it within 2%, that means you have to, these blue lines have to converge down towards the initial, you know, the final value of our system. So that's settling time. And then rise time, this equation is used 1 plus 1.1 zeta plus 1.4 zeta squared over omega n, but that can approximate to this one, 1.8 over omega n. So I won't penalize you for sort of just using this shorthand version in the exam. For a second order time response, if we have an overdamped system, we're likely to possibly undershoot, or at least if we do achieve our final value, you know, it's going to be very sluggish and slow to get there. Right, so this would be an overdamped system, and that's if zeta, our damping ratio, is much greater than 1. If we have a critically damped system, then we're going to basically have a system that converges smoothly to our final value, but again, it's a bit slow. Right, so faster than the overdamped one, but still a bit slow. And if we have an underdamped system, we're likely to get overshoot and settling oscillation. Or if we have too low a damping ratio, we might find that it's unstable and there's actually growing oscillation. Right, so this is showing those three characteristics from one I prepared earlier, but I set zeta to 3 different values. The blue line, zeta equals 2. So that's overdamped, and you can see it's sluggish. The second one, which is the sort of orangey red line, to zeta equals 1, so that's critically damped, converges to the final value, but it does it, you know, a little sluggishly. And then an underdamped system set zeta equals 0.3, and you can see that there's overshoots and settling just like the one we just looked at. And we can expand this. So what we have here is the same system plotted with just different zetas. Yeah, so kind of running through from zeta being very, very low indeed, which is 0.2 here, and then as you go in this direction, your zeta is increasing. This is 0.5 zeta. All right, so it kind of gives you the form of the response of different zetas, and then it goes above 1. So you can see that the highest value is zeta equals 2, and this is just sort of overdamped, sluggish response. And this is, in fact, normalized time. So we have taken time, tau, equals omega n times t. So it's sort of factoring out the effect of natural frequency omega n from the system by normalizing it. Right? So that's why all of these correspond. So it doesn't matter what type of system you have. If you want to use this chart, which you actually provided in the exam paper, you know, if I ask you about what's, you know, you find that the zeta of a system damping ratio is 0.2, and I ask you, you know, what's the time to peak overshoot? Well, you can find 0.2 here. This is the peak overshoot here. Okay, so this is time to peak, and the time to peak is what? So it's about 3, right? But now notice not seconds, it's normalized time, tau. So it's 3, whatever tau is. So to get 3 in seconds, you have to divide by implied t. In fact, we should probably say this is tau peak. Now, this tau is not, it's different to the tau we had before, which is your time constant. Confusing, but that's just how the nomenclature worked out here. So let's call it tau p equals 3. So Tp equals 3 over omega n. So if omega n, like the system we looked at just now, is 3 radians per second, That implies that Tp equals 3 over 3 equals 1 second, right, for a zeta of 0.2. All right, so let's just go back to MATLAB here and say we're going to change our zeta equals 0.2, and then I'm going to say step. I'm going to apply a step input to my transfer function g, and then I'm going to go on my little chart. The charts are the worst aspect of this online version of MATLAB. They don't really, they're a bit difficult to use, but right, okay, not bad. 1.07 is the time to peak here. Right? Peak amplitude is 53% about. At time 1.07 seconds. So I think that's quite good, because I just did a rough measurement here at my 3. Let's see about the peak overshoot. So we could compare that as well and see how it looks. Right, so this is about 1.53 to my estimates. Peak amplitude 1.53. Right, so we got an agreement between our just one little point we took, one case study we took for our standard second order responses, and related it back to what MATLAB told us and showed it's the same. What we've been doing so far is basically determining the transient response of our system using Laplace transforms. And that means that you have to go through the process of finding the output of your system as a function of the input times the Laplace transform of the overall system. And then when you do that, you have to take, do your partial fractions, take inverse Laplace transforms, and so on. It's a tedious job, especially as your systems get larger. So we can, in fact, get transient response a bit more easily using a method of indirect analysis. And that's what we're going to get to, I think, in lecture 6, which we're in lecture 5 now. So in 6, we get to root locus. And then that root locus kind of gives us a way of getting our time response without having to go through all those processes. Basically, you can plot a root locus, measure off values from your root locus, and from that you can directly get your transient response characteristics for your system. So that's just a view of what's coming down the line. Another method is using frequency response. The one we're going to look at is the Bode plots. And so using Bode plots, you can also get back to the transient response of your system. Now, in any of those, in both of those indirect analyses, indirect methods, you need to, what we need to use is what's called the characteristic equation. So we're going to move on now and look at what is the characteristic equation and how do we find it, for a given system. So let's look briefly at the characteristic equation. So if we have a second order system, it could have an output equation like this. Output C is equal to some coefficient A times e to the AT plus B e to the BT plus C. So that's our standard second order. Because it's second order, it has two exponential terms in the, or hopefully decaying exponentials in the response. Right, and if we want to get this equation, actually A, B, and C, all those constants are determined by the initial conditions of our system and the input that's applied to the system. C is going to be a function of the input, really. A and B sort of to do with the initial conditions of the system. The exponential terms, e to the AT and e to the BT, those are entirely a function of what we call the characteristics of the system. So that's to do with, your the properties. If it's a mass spring damper system, the mass, the damping constant, the spring constant. If it's a DC motor system. The second, you've got a second order model that would be to do with the resistance in the circuit, the inductance, maybe the inertia attached to the motor, etc. And so those exponential terms, those transient terms of our system response are entirely determined by the fundamental characteristics or the fundamental behavior of the system. So let's use an example here. Let's get the response to a unit step input of this simple second order system here. We've done this a few times, we've done a few examples of this, so we could run through it now. So we can say C S over R S is going to be equal to, we know what we have to do, take partial fractions because it's already conveniently factorized for us. Right, hang on, let's not go down that road, because what I want to do is in fact first of all say my output is going to be my input times the transfer function. Right, and that's going to be a unit step, which is 1 upon S. So now from this we could take equivalent partial fractions. And I think that gives us a half times 1 upon S minus 1 upon S plus 1 plus a half times 1 upon S plus 2. So if we take the inverse Laplace transform of C of S now, that's going to give us a half, because 1 upon S inverse Laplace transform is 1. So half times 1 is 1, minus this term, which is going to give us e to the minus t, plus half of this term, which is e to the minus 2t, right? So this is the form of our output. When we plot this now, this is what we're going to get as our output. That's exactly what's happened here. You see it leveling off at 0. That's the final value. There's a large steady state error. You can certainly see that. And those terms, the e to the minus t and the e to the minus 2t, both of those die away. Those ones are called transients, and they die away. Now, if we look at the characteristic equation of the system, from the example that we just had, we had our CS over RS equals 1 over S plus 1 times S plus 2. So that means CS equals R, big button, yeah, RS equals our output now times our S plus 1, S plus 2, right? So that's what we have here. If the characteristic of the motion of the system is independent of the input, right, which is what we said. Remember, we said that the if I go back a couple of slides, we said here that A, B, and C are constants and determined by initial conditions and input, right? So if your A, B, and C are determined by initial conditions and input, the characteristics of the system are not determined by the input. The characteristics of the system are determined by its characteristics, right? So we can set our input R to 0, because we said that the characteristic of the system is independent, so if we set it to 0, it's of no consequence to us. For a non-trivial solution, if we set C equals 0 as well, then it becomes a trivial solution. So because obviously 0 equals 0. But for a non-trivial solution, let's say that C does not equal 0. So that means that we have to set the parts inside the brackets, our characteristic element, as 0, and that's what gives us our characteristic equation. This is our characteristic equation. S squared plus 3s plus 2 equals 0. And the roots of our characteristic equation are s equals minus 1 and s equals minus 2. Right? Well, that's obvious anyway, because we started with s equals minus 1 and s equals, or s plus 1 and s plus 2. So obviously the roots are minus 1 and minus 2. We can determine some important things here associated with the characteristic equation of a system, and we basically, having looked at the transient response, or the transient part of the response of a system to a given input, we say really the input value, the initial conditions, they don't matter in the transient part of the response. What matters is these basic characteristics. And we've gone through and we said, well, you could form the characteristic equation like this. You can find the roots, and the roots of the characteristic equation feed into your exponential terms. Now what that means, and this is where we're going to bounce off next time, if either root was positive, then you'd have a growing exponential term, which means the entire system would be unstable. So we're going to now look at one of our tools in our toolkit when it comes to control systems. It's called the Routh-Hurwitz criterion, and it's a way of determining whether a system is stable or unstable, just to determine the absolute stability of a system. And it uses the characteristic equation, that issue. So to assess the stability of a system, we have to know the roots of the characteristic equation. And the general form, as we just looked at, of the exponential term in the transient response is the exponential term with the coefficient of p plus or minus jq. So p, this is your real part, which is going to determine whether your exponential term, decays over time or grows. And then you've got your imaginary part, and that determines the frequency of your cyclical response. And p, the real part, can be anything from 0 to minus infinity to plus infinity, and your imaginary part has to be, that's the strange way of putting it, it should be greater than 0, right? It's positive. Yeah. Well, the complex element in the transient term relates to the oscillation non-decaying, and the real part determines the decay. So we can look at typical responses here, and if we have a positive, like p is greater than 0, so our real part is positive e to the 5t, what we just saw in our step response is going to happen. It's going to grow to infinity. If we have a negative exponential here, because p is less than 0, then it's going to decay. It's stable. If we have a positive p and a non-zero q, then that q, that imaginary part, the 3 here, is going to create a cyclical response, but the 2 in this case is above 0, it's positive, so you're actually going to have a growing or exponentially growing window within which your cyclical response cycles at the frequency given by Q. And then the fourth condition is that you're going to have a negative real part and of course a non-zero imaginary part. So you've got a cyclical output. This transient term creates a cyclical output, but the decay window is, well, the window of amplitude is decaying, and it's settling that decaying, that cyclical response down towards zero as time proceeds. So this is a statement: if a term in the response CT has a negative real part, it will generate a stable contribution. If the system is to be stable, all the terms which make up the response have to have negative real parts. So for the system to be stable, all the terms which make up the response must have negative real parts. If the analysis is restricted then to absolute stability, then we just want to check basically, are there any positive real parts in the roots of the characteristic equation? And that's where this tool that I was coming to, Routh-Hurwitz, comes in. So let's have a look at Routh-Hurwitz. We use it as a tool in its own right, but also we use it as a part of our process when we come to our next major tool, which is using something called root locus. Root locus is called that because it looks at how the roots of the characteristic equation move when something in the transfer function is changed. And the thing you normally change in your transfer function is the control variables, right? The input from your control system. So coming back to Routh-Hurwitz, Routh-Hurwitz is a means of determining whether any of the roots of a polynomial have positive real parts. And in stability analysis, the characteristic equation in the S domain is the polynomial that we have to analyze, right? So Routh-Hurwitz isn't just simply for controls. I think you could use it for other applications, but it's focused primarily on controls. But the method is a method of looking at a polynomial and determining whether the roots of that polynomial have any positive real parts. And of course, the roots are pretty easy if it's just a second order transfer function or a second order polynomial. But if you get a fourth order polynomial or something of a higher order, finding the roots is a little more complex. So this helps. It's like a quick way of determining whether that higher order transfer function is going to give you any instability. So just to rehearse again, the characteristic equation of a basic closed loop transfer function or closed loop feedback system is 1 plus kgh equals 0, right? Why is that? Because that is the denominator. Remember, a closed loop transfer function, if we have our typical setup, all of these being functions of S really, they're giving us our output, and then we've got a negative feedback loop to make our closed loop control system, and this fella coming into a negative side here. So let's call this our input reference, our output C, right? So our overall transfer function C over R is going to be forward path kg over 1 plus open loop 1 plus kgh, right? So we can see here, make this a little clearer, right? What we can see here is that the denominator of our overall transfer function output over input, again, the denominator is our characteristic equation set to 0, right? So set the denominator to 0, and that gives us our characteristic equation. So our characteristic equation will generally be a polynomial, and it'll have this form where you're going to have, you know, some coefficient times s to the power of n, where n is the order of the polynomial or the order of the system. So if it's s to the 3 is the highest order term, then it's a third order system. S squared, second order, s to the 1 or s is a first order, right? So you're going to have basically a series here of different coefficients with reducing order and reducing factor in the polynomial each time, right? So reducing power of the polynomial down to, and you have a constant at the end, b naught, with no s term, set to 0. So the absolute stability of the system can be assessed using this by applying the Routh-Hurwitz criterion. So this is the procedure. For Routh-Hurwitz, the first thing we're going to do is check that all the coefficients are present, apart from B0. This one, it's not so important. But all the other coefficients, you have to have a coefficient for each of these S terms. So if you have a third order, then you're going to have an S, a Bn, or B3, let's call it. You're going to have a B2 and a B1. All of those three have to be present, right? And if we say yes, then we proceed. And then you have to check that all the coefficients possess the same sign. So if it's positive, then Bn has to be positive, Bn minus 1, Bn minus 2, all of those have to be positive, or all of them have to be negative. If they have the same sign, we get a check, and we can continue. If these conditions are not met, then the system has roots that are purely imaginary, or with positive real parts, and it is unstable. So if it fails at A or B, then you've already determined that your system is actually unstable, and you don't need to go further. But if we fulfill these two conditions, we have all our B terms, and they're all the same sign, then we proceed to the Routh-Hurwitz array. It's a bit of a tongue twister. All right, and this is what it looks like. It's a matrix, and the way this matrix is configured is that you list your S powers down the left-hand side, the terms of your polynomial, and then you list out the coefficients within the matrix on the right-hand side. Let's have a look at how this is constructed. Well, firstly, for your S to the power n row, your first term in your matrix is the coefficient from S to the n. Then we skip one, and the next term in your on that row of your matrix is the Bn minus 2. So if we're saying, okay, if n equals 4, then this would be, B4, this would be B2, and this would be B0, right? Or if we were going higher and we said, okay, n is going to be equal to 5, then this would be a 5, this would be a 3, this would be a 1. Right? So you take basically every other coefficient to put in this first row. Second row is basically the same thing. And now you're taking the coefficient from that term, right? So this is a coefficient from, if it's a fifth order, say it's s to the 4, then that s to the 4 coefficient comes here. Then you skip one, you take it from here, skip one, take it from here, and so on. Right? Now, okay, so if we were saying we're going to have n equals 5 as the order of, if it's a fifth order polynomial, then this term here would be our fourth power, and this would be B4, this would be B2, this would be B0, there'd be no other higher coefficients. So I'm just trying to give examples so you can see how it's constructed, and then you keep going down. So in this case, if we said, okay, well, let's keep our n equals 5, a fifth order polynomial, this is going to be 5, 4, 3, right? But now, when we get to the third row, we do it differently. Notice these are C1, C2, C3, so we don't keep taking the coefficients, you just do that for the first two rows. Right? These ones take coefficients of polynomial terms. right? Once you get down to these rows, you use the determinant of 2 by 2 matrices to get terms. How does that work? Well, it works like this. Your first determinant, which is a 2 by 2 matrix, divided by divided by we're taking the first 4 terms, the first 2 terms from the first row, the first 2 terms from the second row, and we're creating this what's called a determinant, which is the matrix 2 by 2 matrix of those 4 terms dividing by Bn minus 1, which is the first term on the second row. All right, and that gives us C1. Now this determinant, you cross multiply these terms and then subtract these. Right, so you cross multiply and then subtract the opposite cross multiplication, then divide by Bn minus 1. That's how you form the determinant, and it's negative. It's a negative, right? It's not positive, it's a negative. So that gives us C1. C1 goes back in here. Okay, so the next C2, which is the second term on the third row, C2 is given by still using the first 2 terms in the first 2 rows, but now instead of using the second 2 terms in the first 2 rows, you use the third 2 terms in the first 2 rows. So basically you're saying, okay, for each term you use the first 2 rows plus the 2 terms on the 2 rows above, up into to 1 to the right from that particular term. So for this one, we're saying, okay, we use the first 2 terms in the row above, or the first 2 terms in the 2 rows above, and the other side of the matrix is formed by the 2 terms up and to the right of the 2 rows above, and to the right of the term we're using. I'm not obviously going into any of the derivation of why this is so, just kind of running through the method with you, which you'll learn pretty easily. And then again, you're dividing it by the first term on the row above, the Bn minus 1 here. Okay, so that's how we form, we continue doing that. So for C3, we'd form the matrix in these terms and these terms. When we go down to D1, we'd form the terms from these and these. The D2, these and these, right? So D3 would be first 2 terms and these 2. And you're always dividing by, so if it's D2, you take these terms and these to form your matrix, and you divide it by C1. So D2 equals minus Bn minus 1, C1, Bn minus 5, C3, divided by C1. Right. So that's how you form your Rathowitz array. And this is where the first column of the determinant is from the first column of the 2 rows above in the Rathowitz array, as I've tried to explain. And the second column of the determinant is from the m plus 1th column of the 2 rows above in the Rathowitz array. Now, the criterion itself says the number of roots of the characteristic equation with positive real parts is equal to the number of changes of sign of coefficients in the first column. So if we go down our first column, every time we go down 1 term, are the signs the same, right? So say we had a situation where plus b plus minus plus. So we'd be okay here, no changes. So this is a change here. So we'd have one change, and then we go down again. This is another change because it goes from negative to positive. So we'd have two changes. That means that we have two positive real roots, and therefore, the system is unstable. But if we were to go down and every one of these is positive, then there'll be no changes. Each of these is fine, and you'd have a stable system. So that's the main criteria, but there are additional theorems which we would apply if we have certain conditions. For instance, if a 0 occurs in the first column, or if there's a 0 row. So those would be additional conditions if you have a 0 or a 0 row, which we're not going to go into actually. But also you can, if you wanted to, just sort of to complete the mathematical definitions, if you have a whole row that could be multiplied by a whole number, then, or divided by a whole number, you can actually multiply it, divide it by that positive number without changing the signs, and therefore without changing any of the logic or the tests of the Routh-Hurwitz criteria. And that might help it to make it simpler to calculate sometimes. So for instance, if we had values for this second row here, which were 8, 6, 4, 2, of course we could divide them all by 2, and it wouldn't change the logic of the Routh-Hurwitz criteria, but it might sometimes make the calculations easier, and therefore you could do it. I don't think you have many situations, you wouldn't really have to worry too much about that in terms of your use of this criteria. An important part of what Routh-Hurwitz gives us, though, is something called the auxiliary equation. And the auxiliary equation can be used to determine the value of a system parameter that would render the system marginally stable. So let's see how this works. How do you form an auxiliary equation? We'll come to that in just a sec, but using the auxiliary equation, you can actually determine the frequency of oscillation in the marginally stable condition. So it's like using what we talked about with setting the damping ratio to 0. So what happened when you set the damping ratio to 0 for your prototype second order system, where you had, let's call it, remember we had stop that. My little pen is messing around here, it's not. Right, there we go. All right, so this is our prototype second order system. If we set zeta to 0, set our damping ratio to 0, then this term will disappear, and you just end up with this this function. You've basically got a missing coefficient for your S term, and that will give you a marginally stable situation, and the frequency is given by omega n. Right? So we already came across this sort of condition because we talked about that a bit when we were looking at the second order system. So let's look at some examples in the few minutes we have left. I'll use the notes for the first one and I'll do the second one by hand. So if we're to assess the absolute stability of this system we have here, it's a closed loop system with unity feedback, no transfer function on the feedback loop, gain of 10, plant, as you can see there, 1 over s into s plus 2 to s plus 3. Right? So we have a third order plant model. So we're going to form our characteristic equation first of all. We know that that is given by, it's a closed loop transfer function, so it's not just the denominator of the plants, don't forget that. You have to say It's a closed loop system, so it's 1 plus kgh, right? That's important to remember. So it's going to be 1 plus k is 10 over g, which is 1 times g really, which is 1 over s into s plus 2 into s plus 3 times h, which is 1. So we can multiply this out into its polynomial form, and now we have our checks. All our coefficients present, but we have a third order system. Got a coefficient which is 1 for our s cubed term, we have a coefficient for our s squared, we have a coefficient for our s, so we can say yes. Are all coefficients positive? We can say yes, it's positive, plus 5, plus 6. Yes, they're all positive. Okay, so we can proceed to set up our array now. So this is our array. We list down the side here all our s terms, s cubed, s squared, s to the 1, s to the 0. Then we take our coefficient from our s cubed, the first term in our first row, take the coefficient from s to the 1 for the second term in our first row. Right, that's our first row form. There's no more terms after that, because if you skip one, no more terms, right? So the second row, s squared term, bring this one and this term to form it. So okay, we got our first two rows established. Now the rest of the rows are established by calculation. So the first term in the third row is the determinant of the first two rows above first column, right? And then the column above and to the right, the two rows above and the column to the right forms the second part of the 2 by 2 matrix to get our determinant, and we're going to divide by our 5, right? Maybe like the bottom left term in our matrix. So if we multiply this, this is 10 minus 6 5s are 30. So that's going to give us minus 20. Divided by 5 is 4. But there's a negative sign here, so it's going to end up being 4. Right? So 4 is the value for that term. How did we get the other terms? Well, the s to the naught term, well, we just actually took our s to the naught term directly and dropped them in. And there's a 0 here because from our s to the 1 term, there's no more terms, right? So we just set that as 0. So this is our Hurwitz array that we've created, and now we can apply our conditions. All the signs in the first column are positive, and there are no sign changes, so the system is stable, and it means there are no roots with positive real parts. Yeah, okay, let me see if I can get this one done. So this one, let's assess the stability of this single closed loop control system. So the first thing we have to do is establish the characteristic equation. 1 plus kgh. Slightly more complex here because we have a controller that's not just a proportional gain. This would be called a PI controller. It's a proportional term and also a 1 upon s or something upon s, which is an integral term. So the characteristic equation is 1 plus 15 into 1 plus s upon 5 upon s times 1 over s plus 1, s plus 3 equals 0. Okay, so if we multiply it out, then we're going to get 15 times s plus 5 on the numerator. So we're just multiplying out by the s basically, over s to s plus 1, s plus 3 equals 0. So if we form our polynomial now by multiplying throughout by the denominator. Then we're going to get s cubed plus 4s squared plus 18s 75 equals 0. So we can perform our checks now and say that number 2 checks all coefficients are present. Yeah, we've got a coefficient for each term. It's the third order, so we've got a third power 3 term coefficient, we've got a power 2 coefficient, we've got a power 1 coefficient in our polynomial characteristic equation. So all coefs are present, and all coefs are the same sign. So we're good on both of those. So we can proceed to set up our array now. So let me just rewrite the polynomial. So we're going to set up our array, s cubed, s squared, s to the 1. I'll leave a bit more space because we need to do the array there. Hey, come on. Just there. Find the street edge. Alright, we'll leave it there. Okay, so we're going to have 1, 18, s squared row, we're going to have 4, and 75. So now for our determinant, we're going to have 1, 4, 18, 75 over 4, and 0. No more terms there. And then 75 for the s to the 0 row. So if we resolve this now, for our determinant, we're going to have 75, let's say minus 75 minus 4 times 18 over 4 equals what? 18 is 72. 75 minus 72 is 3, so it's actually minus 3 upon 4. So in this one we have a problem because we see there's no change of sign here, but we get a change of sign and another change of sign. So we have 2 exclamation marks here, 2 changes of sign. That means system is unstable. So the first thing you have to always do when you're using Rathowitz is to form the characteristic equation, and so we're going to do that now. And the characteristic equation is 1 plus k g h equals 0, and this, of course, this is the denominator of the closed loop transfer function, right? Which is 1 plus open loop. So for this system, this is our open loop here. So we're saying 1 plus our open loop equals 0. And we can multiply this out. So it expands out to, I think, like s cubed plus, I'm just trying to do it in my head here, make sure, s cubed plus 3s squared plus 2s plus k equals 0, I think. So this one's a little different because obviously now the characteristic equation will change a bit in k. So as k changes, then the characteristic equation will change. But let's continue pressing on with Reith-Hurwitz for now. And what we're going to do in this case, in this instance, is basically determine what value of k will cause the system to be stable or unstable. So you notice k is here. K is again a multiplier. So whatever our error is here, our error is multiplied by k upon s. This is, because it's something upon s, this would be called an integral controller. Generally our controllers, this is a slight aside, but just for your information and for some preempting of what's to come, you tend to have a typical controller would be a PID type, but in this case you only have a 1 upon s term, so this would not be a P or a D. This is an I type, an integral type controller. And an integral type controller is like a summer, basically. It adds things up, adds up the error over time to give you your control action. What we call the control action. Let's just call that X of S, right? So our control action is X. So, and that would tend to be a voltage going to our plant, right? So we'd have some voltage going into this plant, and the voltage would be coming out of the controller. So instead of the voltage being the input, or instead of the voltage just simply being the error between the output and the input, now the voltage going into the plant, or the actuating signal, whatever it is, it could be voltage, pressure, flow rate, any of those kind of things, would now be what's produced as a result of the error being multiplied by the controller action, which is k upon s. So that was a little aside, but just to keep reminding you of what we're dealing with here in control systems. So coming back to Reith-Hurwitz, is this system stable? Well, it looks like it's going to depend on the value of k. And once we've determined our characteristic equation, continue with the methodology for Reith-Hurwitz, the next thing we have to do is determine that are all coefficients present. Well, we have a value for s cubed, s squared, s, and k. K could actually be absent, it doesn't matter too much, but the other terms, we've got every, or coefficient for each term in s from cubed onwards. So we can say yes. Next criteria is, are all coefficients the same sign? And again, yeah, we've got positive value of each coefficient. So we can say yes again. Okay, so carrying on our transfer, or not our transfer function, our characteristic equation. Right, so now we can form our Reith-Hurwitz array. So we're just going to put this is our Reith-Hurwitz. So we're going to enter our coefficient for s cubed and then skip one, coefficient for s, then next line, coefficient for x squared, skip one. The next line, s to the 1, this is now going to be the determinant. So we calculate like this, and 0 here, and then in the S0 line, which is a constant, we just have k. So basically, we have to take the determinant here and say that for system to be stable, this must be positive, right? And also from our k here, for system to be stable, k has to be greater than 0. Right, so let's take this determinant now. This determinant is going to give us k minus 6 minus over 3 has to be greater than 0. Implies that k has to be greater than 6. Right? Sorry. K has to be less than 6. Oh, yep. So k has to be less than 6. So that means that for system stability, these two statements resolve into a simple mathematical expression that k must lie between 0 and 6 in order for this to be positive, or every term in the first column to be positive, and therefore for the system to be stable. Okay, so that's our first condition. Next, we're going to form what's called the auxiliary equation. I did mention this before, but we didn't go into it. So let's have a look at this. The auxiliary equation is formed from the s squared rho. So the s squared rho, in this case, would be this row here. Right? So our auxiliary equation, brackets from s squared rho, is given as 3s squared plus k equals 0. Right, so that is our auxiliary equation, and we can learn some more things from that, because what we can do is we can evaluate our auxiliary equation at marginal stability. What's marginal stability? Well, marginal stability is when k is 0, k is 6. Right? And really, k is 0 is irrelevant, so it would be the k equals 6. So that would be the condition. So we can evaluate this situation where we have a marginally stable condition. And so of course, if we want to find what S is at that condition, it's going to be, we have to take the 6 across those, minus 2 root. Problem, because you can't take the square root of a negative number. What's the square root of a negative number? What happens when you have the square root of a negative? Anybody? Imaginary. All right, thanks, Mikkel. You answered for everybody because everybody knew it. I know you happened to get there first. So it's going to give us an imaginary root. So that means that S is actually purely imaginary, and we can write it as I root 2. Right? So this is actually the value of S for which, when we're in this marginally stable condition, when our gain k is 6, then this is going to be our value of S. And this root, being purely imaginary, what's it going to give us? Think about the condition of marginal stability. When a system's marginally stable, what happens to it? Behaving something like this, and I try to draw it well enough. But, all right, so what does that look? It's just look like it's a sinusoid of fixed amplitude. All right, this is a marginally stable system. So over time, our output y is oscillating around some median value, and it's not neither growing nor shrinking. What's the frequency of the oscillation? Well, that's where this comes in. This root 2 is the frequency of oscillation of our system. So our marginally stable or our auxiliary equation really helps us to determine the frequency of oscillation at this condition of marginal stability. So let me go back to my actual prepared PowerPoint and see, right? Well, I did all this already. So we have the frequency, having determined that this is a complex root or an imaginary number that we get for S at this position, at this state of marginal stability. Then we can identify that our frequency of oscillation is root 2. Root 2 is 1.41. So at marginally stable, at a marginally stable state, this system is going to oscillate with at 1.4 radians per second. So now we have two, basic important pieces of information from this analysis. Firstly, what our gain is for marginal stability, and then secondly, when the system is marginally stable, what's the frequency of its oscillation going to be? Let's just look at two other quick things on looking at, this is all part of transient response or time response lecture. After we've looked at this, we're going to move on to the lecture 6, which is looking at steady state systems. So just to kind of wrap this one up. So a couple of other things related to Rathowitz and to analyzing systems for absolute stability. We know that we have to use these two checks. One is that all coefficients are present. The constant term is not so critical, B0, not as critical, but all the other terms have to be present. And then we have to check that all coefficients have the same sign, both all positive or negative. So those two tests have to be done. All right. Now, if we have a system that's like this, like the prototype, this is what we call, remember, what it's similar to, because K in this case instead of omega n squared on the denominator, but this is, let's say, a second order system. And this second order system has a natural frequency of omega n, as a damping ratio of zeta. Right? So that's how we characterize a second order system. We learned that before. So now, if the system, the second order system, is in the state of marginal stability, or if there's a missing coefficient in the characteristic equation, which is the denominator of the closed loop transfer function, right? Then if there's a missing coefficient, then say this coefficient is missing, and we just have s squared plus omega n squared, then that will give us zeta equals 0. So we've got no damping, which means we have a marginally stable condition. And this is the characteristic equation that results. We've basically eliminated the term by saying we're missing a coefficient here for the coefficient of s. So now our characteristic equation becomes s squared plus omega n squared equals 0. So that's where we get this result that I just showed you with the auxiliary equation. That gives us s squared equals minus omega n squared. So s equals omega n. So when we found just now, right, that our natural frequency is 1.41 radians per second, or beg your pardon, that s equals I root 2, which is I 1.4 frequency radians per second, then that is, according to what we have here, that is the natural frequency. Okay. So a purely imaginary root means marginal stability and therefore simple harmonic motion. And that's if we, using zeta equals 0, eliminating this term and getting basically a reduced characteristic equation. There's another rule, which is the negative coefficient rule. So the last slide we were talking about missing coefficients. If you look at the title at the top, it says missing coefficient rule. This is how we treat with a missing coefficient. But if we have a negative coefficient, what's the impact going to be now? So it's the same transfer function, but we've put numbers in. We've put 0.5 and 1 for zeta and omega n respectively. Right, so now the characteristic equation, when we multiply it out, has this negative coefficient for the S term. What's that going to cause? Well, if we wanted to get the roots now, we'd have to use, our quadratic equation, which is minus b plus or minus root b squared minus 4ac over 2a. So we find the roots of our quadratic this way. And as you can see, when we do that, we have a positive real part and we have an imaginary part. So we know because it has an imaginary part, it's going to be, basically that creates oscillation in this system. System will oscillate at root 3 upon 2 radians per second. But also, you note that this term here is positive. Now, remember this S is the root, right? And so the roots are going to give us our general output function. So in this case, it's going to be x out of t equals a plus b e to the half plus root 3 upon 2j plus c e to the half minus root 3 upon 2j. So both of these exponential terms, wait, didn't mean to do that. Right, so both of these exponential terms, they both have positive real parts, and therefore they're both going to grow as time increases, right? Exponentially, in fact. So what we're going to have in this situation is divergent oscillation with a frequency of root 3 upon 2, that frequency coming from the imaginary part of the root. The positive part of the root, well, that means that the real part of the root being positive means that both the exponential terms have positive real parts and they're both going to grow. That's why it's divergent. That's why it's divergent here. And it'll look something like this. Not a very accurate drawing, I'm sure, but you get the general gist of it. Okay, so that's time response.